Hi, guys. Today I want to talk to you about primary productivity. I want to apologize for the fact that there's basically no pictures in this one. It's very boring, but it's very important because productivity is essentially the bedrock of environmental science. It's the starting point we have to go to understand how ecosystems work. And that's basically what environmental science is all about, is how to maintain Earth's ecosystem. So let's just get started with it. So primary productivity is basically it's just the rate at which green plants are able to capture sun energy in the form of sunlight, and store it as chemical potential energy inside the plant itself. And that energy can then be dispersed throughout the rest of the ecosystem by animals that then eat those plants. So basically, anything that contains chlorophyll, green plants, some bacteria, some protists, uh, they're able to take sunlight and through the process of photosynthesis, which I'm sure you learned about in biology, they're able to store this energy in a molecule called glucose. So please, you've got to know this equation. This one is essential that you memorize, okay? It goes like this. Carbon dioxide, which is present in the atmosphere and gets into aquatic systems through diffusion across the water surface. So basically, this is an atmospheric component. It combines, and it's a very low energy molecule. It combines with water, which again is a very low energy molecule. Now, water is present in soils and plants acquired through their roots, or aquatic plants just acquired directly from the water. So this is basically an aquatic source. This is an atmospheric source. And then what they do is plants stitch these two together to form this molecule here, which is glucose. And you do need to know C6H12O6. They stitch it together to form this by taking light energy and using it to break these up and reform them as this. Now, oxygen is basically a byproduct of this. The plants want to make this. They don't necessarily want. Okay, this is not the goal. The goal is to store the energy in this molecule here, and this is just left over. Because if we actually balance the chemical equation, we'd see that we'd need 6 carbon dioxides. We would need 12. So we need 6 water molecules to build this, and what we find is we have left over 6 molecules of this just left over. Okay, so basically, photosynthesis equation, you've got to know that we're taking carbon dioxide, water, using light energy, and storing the energy of light in this molecule here. And this process is called primary productivity. Now, there's a concept that's really important in all of science, really, but it's very important in environmental science, and that's called the first law of thermodynamics. And basically what it says is that energy can never be created or destroyed. It can be converted from one form to another and moved from one object to another, but you can never end up with more or less of it than you start with. And then the other thing is the second law of thermodynamics, which basically says anytime we do transfer energy from one object to another or convert it from one form to another, say light energy to glucose, then some of it is invariably going to get lost or converted to heat energy. So these are 2 very important laws that we're going to be referring to quite a bit this year. And if you've had physics, you know them. Even if not, I imagine you probably had these in middle schools, but it's one we're going to frequent quite a bit this year. So here's what the first law of thermodynamics tells us. It tells us that the energy of photosynthesis has to come from somewhere and go to somewhere. So basically, what I need you to know is this. Energy from the sun comes in as light energy, and it ends up getting stored here as chemical energy in the glucose molecule. This is the high energy molecule here, glucose, sugar. So if I have, and we measure energy in units called joules. So if I have 10 joules of light energy, the first law of thermodynamics tells me that the most joules of chemical energy I could get here would also be 10 joules. The second law of thermodynamics tells me I'm going to get a little bit less because some is going to get wasted as heat. Okay, so here's the deal. Photosynthesis converts carbon dioxide to water, takes that energy from the sun and stores it in this molecule here, which is called glucose, which has this here. You don't need to know that. Now, what plants then do is if they, plant cells have to live, and they're going to live by consuming glucose, just like your cells do. But in order to store it, they can stitch this together to form starches, which are found in like the say potatoes or rice. Okay, so it's just a way of plants have of storing glucose for later use. They can convert these starches back to glucose. Or plants can do a similar thing, but form cellulose. Now, cellulose is less easily digested. Like very, very few organisms have the ability to digest it directly. So cellulose is basically what wood is made out of, what the rigid part of plants is sort of a structural material, very durable. Another thing that plants make is lipids or fats. So sugars, fats, starches, and structural materials, cellulose. Now, one of the reasons this is so important in environmental science is you and I are animals, and animals are made of cells, just like all things are made of cells. And those cells need a constant supply of energy. Where does that energy come from? It comes basically from glucose. And so the process of extracting the energy in glucose and then using it is called respiration. And the nice thing is, it's the exact opposite of the photosynthesis equation. So the respiration equation, which again you need to know, is glucose, C6H12O6, plus oxygen, which by the way were the products in the photosynthesis equation, get converted into carbon dioxide, which you breathe out, and water, which you breathe out, and then energy, which they can be used for cellular metabolism. So when we refer to primary productivity, we're saying is like this is just the fabrication of these carbon compounds by photosynthetic organisms in an ecosystem. So it's basically this is just taking sunlight energy and turning it into all these carbon compounds, these glucose, but also starch and lipids and cellulose. Now, a couple terms we really need to zero in on here. One is called gross primary productivity. So gross primary productivity is simply the rate at which plants capture sunlight energy and convert it into glucose energy. Right? So it's the rate at which plants are making glucose. So I do need you to know this. Under normal circumstances, of all the light energy that hits a plant during the course of, say, a day, about 1.5% of it is going to get converted into the chemical potential energy in glucose. All right, so we're saying like 98.5% of energy just gets converted to heat or reflects off the plants, but 1.5% of it does get converted and captured by the plants as glucose. So we call that amount that got captured and converted to glucose GPP. How are we going to measure GPP? Okay, so energy is measured in joules. And so we could say, well, it's how many joules of energy is captured by a square meter of plant surface or any given amount of plant surface in a given time period. Energy per unit of surface per period of time. So we could say joules per square meter per second. We could say kilojoules per square centimeter per hour, whatever we want, okay? A typical one we use, though, is maybe surprising, is kilograms per square meter per year. And the reason we use kilograms is because when plants capture this energy, they're making sugars, and sugars have mass. And it's a lot easier to measure mass directly than it is to try to measure energy. Energy is just a hard thing to measure directly. Mass, we got that down pretty easy to put on a balance. We'll get back to that in a minute, though, why that works. Okay, so now here, this is what we really need to know about. This is what drives ecosystems. It's called net primary productivity, or NPP. So basically, if you think of it this way, plants engage in gross primary productivity, but they're made out of cells, and those cells have to eat. They have to respire. So plants are going to consume some of the glucose that they produce through respiration. But they don't consume all of it under normal circumstances. They produce more glucose than their own cells are going to eat. All right. Now they can't destroy it, so they have to store it, and that is NPP. It's the stored energy that's left over after respiration. So if we want to just condense this down, and basically when they store it, it's going to be stored as starches and cellulose and lipids. Mostly starches and cellulose. So basically that adds to the mass of the plant. So biomass is a great way of measuring NPP. Plants are going to gain mass over time because they make more carbon compounds than they consume through respiration. That's why kilograms per square meter per year is a way we have of measuring productivity, whether it's gross productivity or net primary productivity. So the formula for net primary productivity, which you do need to know, the net is equal to the gross minus how much energy got lost, or if we want, how much biomass got lost through respiration. So this is the total number of sugars. The gross is the total number of sugars that the plant made, that 1.5% that came in of the energy that hit it, minus the 0.5% that the plant consumed. It ate its own sugars, and that 1% left over, that's NPP. Okay, so under ideal conditions, again, plants, they capture 1.5 of it, they use 0.5 or a third of it, and then 2/3 of it is leftover energy. And instead of getting rid of the energy, they convert it to starches and cellulose, and it just adds to the biomass of the plant. Now, so one way, obviously, of measuring GPP and NPP is to measure the mass, right? So biomass is a great way of doing it, okay? But there's other ways of doing it, okay? Because sometimes this can be a little bit difficult because plants have other things in them other than carbon compounds. They have water in them, for instance, okay? So one way is we can measure how much oxygen change in a system, right? So when plants engage in photosynthesis, they're producing oxygen. So when photosynthesis is happening, the amount of oxygen goes up. But when respiration is happening, oxygen gets consumed. So by measuring the overall changes in oxygen levels, we can infer how much productivity occurred. Both we can find GPP, respiration, and NPP. Or we could do the opposite. We could say, well, guess what? During photosynthesis, rather than producing oxygen, we consume carbon dioxide. So we assume that carbon dioxide levels go down during photosynthesis and they go up during respiration. So if I look at the beginning and ending amount of carbon dioxide in a system, I can figure out how much NPP and GPP there was. And the other thing I could just do is by biomass, right? Because the NPP is just going to be the leftover biomass of the system. All right, so we already did that one here. So basically, we measure biomass. Usually we think if we're going to really measure biomass, technically we should dry the plant out. So we're only measuring the carbon compounds, not the water content of it. And so we typically measure mass in terms of grams or kilograms. So it's often one of the most basic ways of measuring the NPP of a system is in terms of biomass. But we have to be able to be specific. Like it's how much biomass is accumulated over a square meter of ecosystem over a given time period. So the most typical way of doing this is how many kilograms of biomass were accumulated per square meter of ecosystem per year. Now, it's worth noting then that we can convert biomass to joules. Okay, so basically these carbon compounds are pretty similar. You got cellulose, you got starch, and they have a pretty similar energy content. And the energy content is this: 1 kilogram of biomass, wood, potatoes, whatever you want. When you take away the water that's in it, what you find is you get 16,000 kilojoules of chemical energy stored in it. So 1 kilogram of biomass is the equivalent of 16,000 kilojoules of energy. Now, one of the things we like to focus on in this class a lot is basically what we call limiting factors. What limits an ecosystem or a plant's ability to engage in photosynthesis in GPP and therefore NPP? So basically, what do plants need to do their thing? Well, clearly they need light. Without light, there's no photosynthesis. They need water. Okay, so if you don't have much water, precipitation in the case of a land plant, there's not going to be any photosynthesis. Temperature, when the temperatures get cold, it's very difficult for plants to engage in photosynthesis. And the temperature gets warm, it becomes more easy. But if it gets too hot, it gets hard again. Okay, so there's sort of a sweet spot there. And the other one that we're going to talk a lot about this year is nutrients. So basically, in order for a plant to grow, it's not like it just only makes cellulose. It has to make cells that then make that cellulose. And these cells contain DNA and they contain amino acids. And those things contain, if you recall from biology, basically you have a phosphate backbone to a DNA molecule. So you need phosphorus in order to build cells because they have DNA. Amino acids basically have a lot of nitrogenous bases to them. And so you have to have a lot of nitrogen in order to build DNA and amino acids. So nitrogen is really the main limiting factor that we often see in an ecosystem. So if I run out of any of these things, when at night you can't have photosynthesis because you ran out of one of light became a limiting factor, or if it gets too dense in a forest. So light, temperature, water, and nutrients, these are the things that typically limit productivity of an ecosystem. Now, we need to differentiate between terrestrial ecosystems and aquatic ones. They're both important. You're a terrestrial creature, but you need to have the aquatic ones. It's not like we can live in a vacuum here. So in a terrestrial ecosystem, NPP we're going to find is usually going to be greatest near the equator, and it will get less and less and less as we move to the poles. Now, this makes sense if you think that, remember from the last lesson, sunlight is more direct near the equator, so there's more light hitting the leaves, so light is less of a limiting factor to photosynthesis at the equator. Also, at the equator, we often have a lot of precipitation for reasons we'll learn later in the year. And again, so water is less of a limiting factor typically at the equator than it is in other regions of the planet. So those two main limiting factors are not limiting factors. So we find there's a lot of NPP in equatorial areas, especially rainforests. As we go farther up, temperature becomes a problem. It gets cold in the wintertime. It gets dark in the wintertime. The nights are longer, and those things become limiting factors. So we find then as we move polewards, we get less productivity, and as we move equatorwards, we get more productivity. Now, in aquatic episodes, in aquatic environments, I should say, or ecosystems, what we find is NPP is more often limited by nutrients than anything else. So what we find is that water is obviously never a limiting factor in an aquatic environment. Temperature usually isn't either because in very few places the water actually freezes. So if the water is liquid, then cells can do their thing. But what we find is nutrients are usually the main limiting factor. Okay. And so what we find, and light is too. Okay. So if you get too deep in the ocean, there's not enough light. You're not going to have productivity down in what we call the aphotic zone below, where light can't penetrate. But in that photic zone where light can penetrate, what we find is this: nutrients are the main thing. Nitrogen and phosphorus, and mainly nitrogen. So because in these ecosystems, the nutrients tend to be in the bodies of animals, and they sink out of that photic zone where light can penetrate. And so the aquatic plants, they can't get nutrients, so they can't grow. So we find is any places where the aquatic ecosystems have nutrients coming in, say from rivers, or a process called upwelling that brings the nutrients from down below back up. Where we have that happen, we tend to get a lot of productivity, as much as you can get, like, say, with a rainforest. So what we find then is the places where we get our most productivity in the oceans is going to be in where rivers meet the sea. These are called estuaries. In places where we have upwelling coming up, and in coral reefs. And so this last thing is just a table showing you, basically giving you a comparison. So let's just compare, okay? A tropical rainforest has an NPP of, we'll say, 9,000 kilocalories per square meter per year. Look, an estuary, same thing, okay? So this is an aquatic one that's just as productive as tropical rainforest, can support just as much life. But what we find then is if we go to a savanna, that savanna we're going to learn is a place where there's less water. Well, now water is a limiting factor, so I get a lot less productivity. If I go to, say, here in Korea, a deciduous forest, there's quite a bit of productivity because there's plenty of light, there's plenty of rain, but we don't have all year sunlight, right? So the sunlight becomes limited in the wintertime, so we have less of it. Oops, I just lost that. Anyway, I'm going to leave you out here. I know it's a little bit longer than I meant for it to be, but thanks for watching, and we'll have some fun activities to do with this when you come to class tomorrow.